Okay, so hello and welcome. So for today's session, we are going to have the shear and moment diagrams now applied in frames. Of course, previously we had already captured the procedure of shear and moment diagrams applied in beams. So to have a recap, actually we have two approaches in doing that. We have shear and moment by equation method, wherein we have used x, where x is moving at every segment of this beam, or that is not constantly loaded beam here. So x will move to the boundary of AB, boundary of BC, and the boundary of CD. And then we take the section per section and then label Vx and Mx, and then just write Vx as summation forces x, where shear values are obtained through this equation. And then Mx is summation moments. And consider a sign convention that we have a positive moment for a concave upward fiber and a fiber that is concave downward is designated as negative. So for shear at x, of course, we know that we have positive upwards and negative downwards. So as simple as that. So that is for the shear and moment equation by equation method. Okay, so important points: that at shear is equal to 0, moment is at maximum. And then for the second method, of course, this is by graphical method, wherein we note of the pointed loads will just either increase the ordinates of the shear diagram or decrease it. Okay, and then as for our another basis is that if we have distributed loads, we'll just have to refer to the area of that distributed load, and this area shall be added or deducted from the existing ordinate of the shear diagram. And for the curve or the connecting curve between 2 points, we note that referring to the load diagram, we just have to determine your curve whether it is increasing or decreasing, and the relationship with the connector on the shear diagram is an inverted logic, wherein if this is increasing, we're going to use concave downward connector, and if we have a decreasing, of course we have a concave upward connector on the shear diagram. Now if we have to refer the shear diagram and the moment diagram, say we have here another column. If we have an increasing shear diagram, your moment diagram will be having a concave upward connector between two ordinates, and the concave downward for a decreasing shear diagram. And as for the ordinate of the moment diagram, of course our concern is the location of the maximum value of the moment diagram, and that could be obtained by locating where shear is equal to 0. And usually it is done by ratio and proportion, or if it cannot be done by this, of course we go back to the equation Vx and then just equate it to 0 and then locate that value or the point where the shear is equal to 0. So of course the moment diagram shall depend on the shear diagram, where the area of the shear diagram, wherein we note here that it is the sum of the areas from left up to the right portion. So we start from left to right, and that will be equal to the ordinate of the moment diagram. Of course, we note of the positive area, whether it is negative area. Of course, we should consider that in the calculation of the ordinate of the moment diagram, and then apply this connector, or if we have an increasing concave upwards, decreasing concave downward connector. And for the curve, of course, we'll just have to add 1 degree per load diagram and V diagram, and moment V diagram to the moment diagram. So meaning, if we started the flat line on the load diagram, say a 0-degree curve for the load diagram, it would become 1 degree curve on the shear diagram and the 2nd degree curve for the moment diagram. So in whatever situation, whenever we started with the curve on the load diagram 1 degree, of course, it will follow that we'll just have to add 1 when shifting to another diagram. Okay, so if it is 1 degree, it will become 2nd degree on the shear diagram, and eventually would become 3rd degree on the moment diagram. So that's the procedure. So what is new in our topic, shear and moment diagram in frames, is that the sign convention for the moment values is now different for frames, because frames includes vertical or diagonal members, unlike in beams that your member is always horizontal. So we base our sign in your beams as positive, your fiber is concaving upwards, and negative if your fiber is concaving downwards. So this time, for frames, we're gonna consider an outwards or an inwards orientation, wherein we have positive for going outwards fiber, and of course negative fiber going inwards. So how is that? If we apply here a rightward horizontal load, of course the effect of this to the column will be your column is going inwards, so that will be considered as a negative sign for the moment. And then another load here horizontally towards right in this right column here, it will have a fiber going outwards, and that will be considered as a positive moment. So likewise in your beam, if we have a couple C here, what would be the rotation or the effect on this? So of course, if you're going to cut this one on this section, considering the left portion, of course we will be having this loading, assuming that this is a pin connection, and it will also contain a horizontal loading here. Okay, of course, if we cut a certain section, there will be an internal shear that is developed, an internal horizontal force, say H, and an internal couple here. So if we take moments at this point, what will be the sign of C? So we're going to pin this and then apply the C. And what will be the behavior of your frame? It will have a orientation wherein your fiber is going outwards. So that is the effect of C. Okay, if that is going outwards, we take a positive sign to it. And for the reaction, this is going upwards. So if that is going upwards, again, your frame would tend to have a fiber going outwards that will be considered as negative. Unlike here in the horizontal rightwards here, it will have a fiber going inwards, so that will be considered as negative moment. So that is how to do it. And of course, normally for the framing system, we usually separate the beams and columns, wherein it is being detached accordingly. or separated from each other, or unpin your frame, and then label all the forces involved. External forces first, and then we go to the internal forces. So of course, if it is a frame, usually it has three components or internal forces developed depending on the loading. Of course, if we have a horizontal load, it will include now a horizontal internal reaction on that. Okay. So if we are going to assume a horizontal HB here, it would be the same horizontal HB on this beam here. However, it will be oppositely directed when it is transferred to the member. So as for the shear at B, so this is downwards here and it will become upward here, but the same or equal in magnitude. Same true with the moment at B. So if this is clockwise, this will be counterclockwise. So this joint would also have its internal forces develop. Of course, we would want it to reflect all of the loading externally and then establish these internal forces. We place there the external force couple C, and then the three internal forces: moment, horizontal force, and the shear force. Okay, so again, this will transfer to this column here, the same magnitude but oppositely directed. So VC will be going down. Horizontal force at C will be towards left, and MC will now become a clockwise moment. Of course, finally, we will place all the necessary external load that is applied to the frame, and then all of which your procedure will follow according to what we have discussed in the procedure of shear and the moment diagrams applied in beams. So this is just adding the ruling of the sign convention, the outward and the inward, and then of course section per section of the members here, the vertical and the horizontal members, and then we will adopt similar procedure. So moving on to the example, we have here a frame supported by a roller and a pin. This time there will be vertical force here, or vertical member AB, and these are subjected to 3000 horizontal and 5000 going downward force at B. So the first step is to determine the reactions. So RA will have just one, or that is vertical RA here, and then C will have two. Since this is pin connected, it will have a horizontal force RCX and a vertical RCY here. So RCX is obviously, if we take horizontal equilibrium equation, we will just conclude that RCX is simply equal to 3000 pounds. Of course, RE and RCY will be solved out of summation moments. So we do that. Summation moments at E, we have 3000 times 6 less 15 RCY less 3000 times 11, and that will be equal to 0. We compute and we will find RCY will be equal to negative 1000 pounds. So negative is an indication that we have assumed a wrong direction for RCY. So RCY is supposedly going downward. So anyway, we'll just maintain here the same figure, but in our analysis along, we are going to always carry the sign here and first maintain the direction. So we take moments at C here, and we have counterclockwise 5000 times moment arm of 15. Another counterclockwise 3000 times moment arm of 5 plus the RA, which has clockwise rotation, times 15, and that will be equal to 0. So finally, we have a positive 6,000 pounds for our RA. So to check our reaction, of course, we're going to perform summation forces along the vertical axis. First, we have the 6,000 going upward, that is the RE actually. We're going to less this downward 5,000 here. And we place here positive sign for RCY, that is going downwards. But carry the sign of your RCY. Okay? And that will be equal to 0. Of course, we will notice that it is really equal to 0. So we are now assured with our reaction A and RCY. We can now proceed to our analysis. So the first step is to unpin all the members. Of course, we only have two members, horizontal and vertical, members AB and members BC. We place the loadings. These are external loadings and the distance there. And of course, we are going to place here your internal loadings. So if we're going to cut this member, what will be the effect of these external loadings internally? So obviously, we are going to have downward 6,000 here as the shear or the reaction at B or internally. Of course, we can do it if we take an assumption of the direction, but this time your AB consists only 6,000 going upward. So it is so obvious that your internal vertical force here along B will be going downwards. That is equivalent to 6,000. Similarly, 3,000 is also rightwards here. And obviously, this will have a leftward 3,000 there. What about your moment at B? So if you're not confident enough, you may assume direction here and we will just reflect in your equation. So in this particular section or member AB, if we pin this, okay, if we pin this at this point, then we'll be having MB here, okay. So moment at B, obviously 3,000 will cause a rotation that is counterclockwise. So obviously MB should be clockwise. Why clockwise? Because it will resist 3,000 rotation. Okay, so if we're going to compute your MB by FBD of AB, we have summation moments at B. So we're going to pin this 6,000, 3,000, and 6,000 here will have no rotation because there is no moment arm. So it will just coincide to this point. Obviously, 3,000 will just have the rotation counterclockwise. So counterclockwise, negative 3,000 times 5, and then plus moment at B, that is equal to 0. So moment at B is equal to 15,000 pounds foot. So we have here a positive. So meaning your MB is really going clockwise. And then these internal forces will just be transferred here on this horizontal beam. So if we have a leftward 3,000 here, there will be a rightward 3,000 on your beam. Same true with your 6,000 going downwards to become upwards 6,000. And if your MB is clockwise, this will be counterclockwise 15,000. So of course, we're going to place here also the external force on the joint itself, that is going downward 5,000. RCY here is going upwards, however, negative. And then RCX will be leftward 3,000. So we have actually completed your load diagram. And if you have the load diagram, of course, it's so easy to establish your shear diagram. So we are going to adopt the most convenient here, that is by graphical method. We first consider the shear diagram. Okay, from the load diagram, so on this vertical member AB, we will just be concerned with those perpendicular forces, because eventually 6,000 here will cause no effect in terms of shear of this AB. 6,000 is actually axial for AB. So those horizontal forces will have a shear effect on AB. So from 0 to 6 here, there's still no loading. No loading, and then it will push 3,000 shear here inwards. Okay, so we will be having here 3,000. And then it will remain to be 3,000 here. By the way, we indicate that by negative sign. Negative 3,000, and then eventually it will go back to 0 value here. So your internal forces does the balancing of the joint B, where it will turn to 0. So moving on to the horizontal member, so perhaps you can move this. So we have here the column labeled with your dimensions and the shear that was established. Okay, so for the horizontal member, this is actually 15 feet. Okay, so we note the load diagram because that is our basis on that member BC here. Okay, so starting with your vertical here, of course, again, 3,000, the horizontal 3,000 will have an actual effect on this BC. So it has no shear effect. So only the vertical will have the shear effect on the horizontal beam BC. So we take all of the vertical forces starting at B. Starting at B, we have upward 6,000 and downward 5,000. So this will sum up to 5,000 1,000 going upwards. Okay, so it will sum to 1,000 going upwards, and then it will maintain to be 1,000 up to point C. So until point C, there is a going upwards 1,000, that is negative 1,000. So if we have a positive or going upwards, we will just have add but carry the sign. So adding and carrying the sign, 1,000 minus 1,000 is equal to 0 here. Okay, so it will yield your shear diagram to 0. So this is now our shear diagram. And from the shear diagram, we are just concerned with this area here. Area of AB, area of BC, and of course, the couple that will be developed in per joint. Okay, so let's see. So MB here will have a clockwise moment equivalent to 15,000 pounds per foot on the column AB. So we're going to place that on the column, and then for this, we have a counterclockwise on beam BC that will be just equal to 15,000. So we have completed our basis in the moment diagram, so we're going to draw now. So the M diagram, we have the column AB and beam BC. Okay, so the ordinate from this point up to this point is still 0 until there will be an area from this point up to B, and that is rectangular area. So if we have rectangular area, we just have to get the area 3,000 times 5, that is negative 15,000. So we are going to place that inwards. Of course, we have to move this. Okay, so we place that inwards because that is negative. 15,000. And the connector, so if, as we can see, this is a flat or horizontal or vertical line, it will just be a first degree curve, or that is straight line. And then 15,000 will close to 0 because of this 15,000 here. Okay, that will tend to have the effect. So what is the effect of 15,000? That will be outward. Your fiber tends to have an outward effect. If you're going to apply 15,000 here and then pinning your frame here, so apply 15,000, of course it will have a outward orientation of your frame here. And that positive, if we have an outward, of course 15,000 plus positive 15,000 is a 0 moment here at B. Okay, so moving on to our beam at BC. First, we have the couple here. 15,000 will have an inward orientation of your fiber. Okay, so that will be negative. 15,000 there, and then we add the area here, rectangular area, 15 times 1,000, that is 15,000. If negative 15,000 plus a positive 15,000, will have 0. 0 here, and the connector will be just straight line. Okay, so your shear and moment diagram, if it will yield to 0, it is an indication that we are doing it in a right way. Okay, on the other hand, if it will not go back to 0, there is something wrong along your solution. You must have to check it. Okay, so here is our moment diagram now. So this is it for this problem, and we can expand this by doing a more complex frame that involves the establishment of shear and moment diagram. Okay, so we would like to reiterate again that you should have practice on problems that are available on the PDF file I've sent you previously. Okay, so have more practice, and we will proceed to another example. Thank you.